presentation. So, a catchy title. I've inspired by Stephen Feltz's standardized objects now. And compared to objects, I find that I use strings much more often. So if we need to standardize more string functions, I think it's more important. And so the question is there a problem at all? Many claim that Folk lacks string support, and everybody has their own string package, which seems to, many people have their own string package, which seems to which indicates that there is something missing. And I also find that I often need more than what's in the standard. So the goals of having additional string words, at least the goals I would see, is ease of use and integration with the existing stuff we have. And what is the existing stuff we have? We have the string word set, we also have some other words, but I specifically looked at the string word set, which has words for creating substrings, dash trailing, dash string. I'm wondering where put search, so search should be here too. Somehow I forgot that. Anyway, so search too. There's words for inspecting strings, or there's compare for inspecting strings, and you can also consider search as being used for inspecting strings. There are words for writing into pre-allocated buffers, blank cmove up. There's sliteral for compiling a string, and what is missing is words that allocate by themselves, which, I think that's a conscious design decision. So, for example, one thing that I find missing is a string concatenation word. So, but of course you can do that with move, something like that. So the main design decision, I found, so basically at the start of it, of this whole thing, I thought, I wasn't really very clear about what I thought is a good way to deal with strings, and at the end I had some ideas, and I'll give you some of the considerations I did during thinking about this. So main design decision seems to me to what to do about buffer allocation. So there's the pre-allocated buffer approach that's used in basically all standard, current standard words. There's manual reclamation, where we basically a word like that the string concatenation would allocate by itself, and some user of that word would have then to free it. Or alternatively, one could also use region allocation. And finally, there's automatic reclamation in the form of garbage collection or reference counting. And I talked a little bit about various allocation modes in my other talk. So let's take a look at the pre-allocated buffer regime. So there's a new standard word called substitute, which actually follows this regime, and basically we want to substitute within this string, and the output is in this pre-allocated buffer, and this describes where basically the output string. So the output string is it starts at the same address as this buffer, but the length may be different, of course, and of course the length shouldn't be U3 shouldn't be larger than U2. So basically that's what this first sentence says, and the rest of it is all about dealing with buffer overflows, or preventing buffer overflows. So it says an ambiguous condition occurs if the resulting string will not fit into C adder 2 U2, or if C adder 2 is the same as C adder 1. So basically we get an ambiguous condition if we have a buffer overflow. So actually this word is allowed to overflow the buffer because in an ambiguous condition it can do anything. The return value n is positive on success. A negative value for n indicates that an error occurred, leaving
what is the number of substitutions? I don't understand what n counts.
That's actually, so basically this word substitutes certain things inside this string, and so percent name percent things, and the number of the things it substitutes is n.
Plus,
But
there are another 4 paragraphs to this definition.
I just put in the stuff that's relevant for talking about pre-allocated buffers. So, so this basically my point in this whole discussion is that this pre-allocated buffer makes for a complex specification here, and we see here some code usage, except that I didn't use substitute. I did have my running example is going to be using a string concatenation called S+, and I will concatenate a directory, a slash, and the file name. So you get basically I'll construct a file name in this way, a path name, by concatenating a directory name, a slash, and the rest of the file name. And here's how this is with if we use an S+, that's basically designed in this way. So we have here first string, then we have the second string, here we have the target buffer, and here we have the recycling string. And we have an n, which tells us if it's negative that the buffer was not big enough. And the code is that we basically create space for one buffer, another buffer. We pass the directory slash and the first buffer to S+, and then we have to check the end result and do an abort if it's too short. If the buffer is too short, or I mean, that's not a very nice way of handling it, but it's certainly the shortest one. We might also have some way of handling it by then allocating a bigger buffer and trying it again and so on, but that would be even longer. And here we, as a result, we then have here this thing, and we append then the file to this, and we store this whole thing in buff2, called S+, and again have to handle the case that the buffer is too small. And eventually what we do is we use this whole recycling string in OpenFile.
Can you do an in-place replacement with this? So instead of using buff2, reuse buff1?
One can think about that, but that's not my main topic here. It's just so maybe one could write S+ in a way that reusing buff1.
So S+ is not in the standard?
No.
Oh, okay.
So that reusing buff1 would be okay, or actually what I've been using is two words, one for doing a new concatenation and then appending to an existing concatenation, and one could use that approach here too. But yeah. So instead of using a pre-allocated buffer, we could actually let S plus allocate the buffer by itself. And the nice thing about that is that determining what the right size of the buffer is done in the allocating word, and the user doesn't have to deal with that. I mean, for S plus, for concatenation, it's actually pretty easy to determine what the right size of the buffer is, but for example, for substitute, it's pretty much, it's not practicable. So, and in general, it's not practicable. So, so actually, here, this S plus has a different interface. We get the first string, we get the second string, and out comes a third string that's allocated, and that then has to be freed eventually. So here is what we are doing here. We get the directory, we get the slash, and we get the file name. We concatenate the slash into file name, and then we have to remember the address of the resulting string, because we eventually have to free it. So that's what's done with over 2R. Then we concatenate directory with this stuff. And since we no longer use the concatenated slash and file name, we can now free the buffer of this first S, allocated by the first S plus, which is down here. Then, okay, now we have another buffer coming from the second S plus. We eventually will have to free 2, so we have to remember 2, which is down here. Then we use the whole thing with, for an open file, which is down here, and eventually we have to free this buffer, which is down here. So what we see is it's shorter code than the pre-allocated buffer, and we don't really have to deal with the case that the buffer is too small, but we still have quite a lot of work to do for freeing the resulting buffers. So we can do, yesterday I presented regions, and here's a version that uses regions in connection with quotations. So we have here, basically, here we say, here's the meat of the S plus part. So the S plus has exactly the same signature as for the allocate version, and we also have to make sure that we freed ourselves, but we manage the memory through regions. So here we have our three strings that we want to concatenate. We concatenate these two strings, then we concatenate the result with this with the result, and we are saying that we are doing it in a specific region with region, and basically eventually we get out a string that contains the concatenation of this all, and it's allocated in this particular region, and the intermediate result here is also allocated in this region. Here we use the result by doing read only open file, and what's going on here is we have another quotation around all of this, and here we have a word that gives us a region and basically passes it in here on the stack, so it can be used in with region. And when it's done, it frees the region. So that's a more concrete application of what I talked about yesterday. This doesn't look really shorter than the allocate free thing, but the reason for that is that we only have two S pluses here. The thing is, if we make more, we have more allocations, this overhead doesn't grow larger, at least as long as we use only one region. Whereas if we use, for example, many S pluses with allocate, we would have to do. So here's the ideal, what we would get with garbage collection. So we still have the same signature. We get two strings for S plus, we get two strings, and we get another string out. And the nice thing with garbage collection is that the garbage collector does the memory reclamation for us. And the code is basically we have the three strings, we do two S pluses, and then we can just use the recycle, and we don't need to care about reclaiming the memory. The problem, of course, with garbage collection is that it's a mess to implement. I've talked about it yesterday, so we probably don't want to go there. But it would be very nice. Reference counting is especially usable in connection with strings, because there cannot be cyclic. So strings are not do not contain pointers, so there cannot be any cycles of strings. That would be a problem for reference counting. And the other...
Anton, sorry,
yes.
could you say that again?
So one problem with reference counting is if you have a cyclic data structure, so one pointer pointing to the next and so on, basically,
Okay.
and you have a pointer into it, and you delete the last pointer, it won't get free because the cycling makes sure that all the references have at least count one. And this doesn't happen with strings because you don't have pointers within strings. So you can use reference counting for strings.
Pointers within.
Pardon?
Okay.
And the typical use that you would do of reference counting for strings is you would have a string stack. You would have special words for everything that you do with strings. You would have special words, and this is what we see here. So we have S plus that takes a string 1 from the string stack, string 2 from the string stack, and produces string 3 on the string stack. And here we have a dir which is a constant or value or something, a string constant or string value, which used to be a 2 value, a 2 constant, and here it is a string thing. We have here a special string literal word, here another thing that produces something on the string stack. Here we use S plus to actually add them or concatenate them in the string stack. Another S plus, and here we then have a string variant of open file, which actually takes its string parameter from the string stack. So basically what this means is if you want to go with a special string stack, you can use reference counting, or alternatively, if you use reference counting, a natural way to deal with that is to use a special string stack and special string words, but we basically have to have new string stack specific things of all words that deal with strings, and which is very bad, very low on the integration goal. So which brings me to the next topic. So basically until now I've talked about buffer allocation. Next topic is the on-stack representation of strings. The 494 standard used the preferred the C adder U representation, and I preferred actually 2 because it's very nice and flexible and allows very flexible substring operations. The main disadvantage is that it takes 2 cells on the stack to represent the string, also 2 cells in a variable to represent the string, and therefore many people still prefer other representations. One popular one is the counted string, and the disadvantage is of the classical counted string is that it only allows up to 255 characters, and it doesn't allow substrings. I think there have been some people who have proposed using cell-counted strings, which would have a cell count at the start.
Sorry, could you just re-explain the point about no substrings? Could you re-explain that?
Well, if you have a counted string and you want to do a substring of it, you cannot just you have to make a copy to create it. You cannot say, okay, I give five characters in and have a counted string there.
So sharing a string is a good technique if you know that you will not write into the string. So you can just with another 2 values you can have an arbitrary substring with the first 2 cell approach.
Yeah. So yeah, so basically that one could be alleviated by having another string representation. That one is there. So basically, if you want to do a substring, you get into the buffer allocation issue. Then there are some people who actually advocate using zero-terminated strings. The disadvantage is that you cannot have a null character inside the string, and basically you cannot use this stuff, these words for binary data, and that's the reason why C, which is actually using zero-terminated strings by default, has basically 2 copies of each library function. One copy that does a zero-terminated version, and one copy that has something like the C adder U representation. For example, you have put S for the, or F put S for the zero-terminated version of file output, and you have F write for the binary version. And also substrings are severely limited. You can only, without having a copy, in the zero-terminated strings you can make something that's at the end of that string into a substring, but not anything else, because you would have to write the 0 somewhere in the middle of the string otherwise. If you use a separate string stack, you can use any internal representation. You can make your string stack contain things, whatever things you want. And one thing you would probably do is to maintain a reference count. One other issue I came across when considering this topic is regular expressions. Basically, there are lots of languages that are called scripting languages that are pretty good at dealing with strings, and they all have regular expressions for matching things. I looked at the stuff that's in awk, which is one of the most memorable scripting languages. and I found that what awk does with regular expressions can be done with one particular word, so based on one particular word, and I'll explain it in a moment. Basically, what is a regular expression? It's something that describes a pattern. So you can describe a number of patterns with a regular expression. Not everything, but it's apparently good enough. And here we have one that describes a pattern that we have a digit, so anything from 0 to 9, and we repeat it one or more times. So that pattern describes all strings that contain one or more digits. And our search regex is a variant of search that searches for regex. And if we apply it to this string here and search for this regex, we find this pattern. And if we then searched for the rest, we would find, with the same regex, we would find this pattern. And the interface that I have here is I pass a string to be searched in, a regex as a string, and finally, and then as output, I get the first part before the regex, then the matched string, and then the stuff. The final part after the regex, and I get a flag, which tells me if I have actually found a match. So if I do this string search, so this search regex in this string for this regex, and type the result, the CA5, U5 is this, so basically this, and CA4, U4 is this, and CA1, U3 is this.
You need to insert your drop bar for the first CO.
You have ignored the flag.
You need a
Oh
drop
yeah,
in front
very
of the
good
first
point,
CO.
very good point, yeah. So that, I need to insert a drop here, or dot, whatever. What awk does with regular expressions is to split strings, either by using the regex as a pattern for matching the separator, or it also has another way of splitting strings by using the regex for matching the fields that the string is actually matched, split into. So one can, with search regex, one can do both. And the other thing that it does is to replace patterns with something else, and one can use search regex for that too. So basically, that would be a primitive. It's for doing such things.
I think it's not a well-factored primitive because usually you compile regexes.
I considered that too, but I didn't want to actually overload the presentation. You find that idea in the paper. I'm not sure if the interface I designed for that is good, but we can discuss it.
The other thing is that usually when you have this parents in regex, and you can have more than one string matching in one regex, and then you use some sort of array. Instead, it's this \1 to \9 to extract the found strings, and so you don't have to return the actual string. You just, when you want to see it, you need to have this parent in the regex.
Yeah, well.
Not in Orc. Orc
Not
is a
in
really,
Orc.
really old regular expression
Yeah, but
that nobody ever uses anymore.
Yes. So
I use Orc.
I would not look at all.
No, you probably use Gork, not Orc.
Yes, yes. I also looked at Gorks.
But the Orc regex is very basic.
But yeah, I mean, I didn't want to so the point I want to get across is that we probably want to add some regex capability.
Yeah.
It doesn't need to look like this, but yeah. Yeah?
Did you evaluate the version not making the separation of the string, but simply saying where you found it and how long? So, because
No, that's basically
That's
it.
what this does.
So I get this one out, I get these ones out as well. Of course I could compute this and this from from this and this, but I think it's more convenient to actually directly have it.
your output is now strings, and my question is, what about the version when you say what you were searching with your regexp? Just give the place you found that
Yeah,
expression.
that's it. So that's the start. So basically, in this, it points to here,
Oh yes.
and the length is 4. So that's the place where I found it. That's the length.
So that's a nice thing if you have this address and count representation with 2 items
Yes,
on the
yes,
stack.
yes.
You can have one stack and you can have several substrings without copying the content of the string.
Right. So the disadvantage of the CRU representation is that it takes that it has many that it has 2 items on the stack. So the question is, what can we do about having too many stack items? And my my solution to this is to actually use implicit parameters for some things, and here is a large example of using regexp, and I have a new regexp version that actually has an interface with here stack items. So I do a parse regexp, which takes the regexp and takes the input string implicitly from the current input buffer. And here I have the first output, which is the thing that is passed by parse regexp, so which doesn't match at first. This is the matched string, and the rest of the string is left in the input buffer. So if we want it, we can just say source to in/string. Here we have a word that replaces in the current input every number, every string of digits with this num string, and what it does is basically it takes a string from the input buffer and it prints the result on the output. And this uses a begin, while, repeat loop for doing it. And we can actually test this and show that it's output, that it works. execute parsing that takes a string and turns it into the input buffer, and then calls this word REPL num1, which is this word. So basically what we have here with REPL num2, we have a word that we pass a string to, and it replaces all the numbers inside with this num, and outputs the result to the what's it called? User output device or something like that.
Terminal?
Basically to the
Console.
terminal, yeah. And here we have, but we may want to have the result in a string. What we have here is we have another word that that's called toString execute, and we pass it an execution token, and what it does is everything that's being typed or something by this word actually goes into a string, and we get out of toString execute we get that string. So here the overall stack effect is that we pass in the input string, and we get as a result the output string, and and the point of all this is that we have used implicit parameters. We used the input buffer and turned the input into this input buffer using execute parsing, and we used here as output parameter or as implicit output parameter, we used basically the output the normal output device, and we used toString execute to turn this into some explicit string. So, and in this way we can get rid of some of the stack noise that we have to deal with. Yeah, here we have an application example. So if we then call have a string, it's the same string as above, and we call REPL num this word here, then type the result, we get as output basically the same string, but all the numbers are replaced with this string. So my conclusions. So in the beginning, I didn't really know what I would get to, but the fog has cleared, and so my current thinking about strings is that we probably want to use region-based register allocation for dealing with the buffer allocation problem. The string representation should continue to be C/U, and I think it's a good idea to use execute parsing and toString execute to reduce the stack load, and we want to add something for dealing with regular expressions. Thank you.
Who has questions for Anton?
Did you consider starting this at the other end, so to speak, where you said what are the high-level functions, and then working back from the way you build it? Because my observation of the way people use string packs is they're handled by application programs in the main who are not gurus by any means, and they can cope with a string object identified by one cell, but they should never see any more than that. It's actually essentially everything needs to be inside that object. because then it makes it fairly straightforward. The downside of that approach is very much that the string package tends to be slower. But that's just another gigahertz or two.
Well, I actually have been using strings for a long time, and I really have a hard time seeing how any particular application use that I made could be turned into things that are much higher level than what I presented. So maybe I'm a too low level person, but I mean, there are certainly string packages that do string stacks and whatnot, and which may be a higher level, but I'm not sure I would want to use that.
But you put up at the
But
beginning.
it would be useful for my users.
You put up at the beginning that one criticism is that Forth doesn't have strings, or people say that Forth doesn't have strings. I mean, that's the point that's being addressed here. So I don't know anything about Forth, but I see it doesn't have strings, and when I look, they seem really complicated. That's the problem. That's the problem statement, I guess.
Yeah.
I think the main interesting idea from producing strings is to use the terminal words like type, emit, and you can also use dot and everything, but produces terminal output, to produce strings. And this makes producing strings a lot easier, this to-string execute. And it's not so much about what kind of mechanism inside to-string execute is used if you have, because the string actually, the way to construct the string is implicit. It's no longer explicit. You don't have a string object. You have a terminal that in the end will be returned as string. And that means you don't have mental clutter because you use the same words you use to display strings to produce strings. You can test your words which produce a string without this to-string execute wrapper and see what they will produce immediately. It's much easier to work with. I modified Anton's libcc, which produces a lot of strings into a file, to use this approach, and it became much easier to read and to maintain afterwards. That's the most important point, I think, is use the terminal words to produce strings. You have all the power to call functions which convert things to floating point, to integer, or whatever string you have, without writing new code, because it's already there. If I have a string package and I want a floating point number inside, how do I do this without using the terminal words? I would have to make new words, create a floating point string on the stack, and then add it to the current string object, which also flies around on the stack. I don't want that. It's too much stack clutter.
You end up with a whole parallel universe.
Yeah, yes.
Yes.
Whole parallel universe. It doesn't
Can we just
work.
take one more point? I think you have a point.
Yes.
And then we are running about 10 minutes late, so we'll just take one more.
Okay, try to make it short. I always question the use of regular expressions in languages, because for me it seems to be that the developer, the programmer, is forced to learn just another language because regular expressions are another programming language. I know they are very popular in other languages, but maybe there are better ways that are more, that don't force the developer to just learn another programming language again and merge that again. It's good for people who know regular expressions already from Python and Perl and Ruby and so on. They probably can cope with it. but I found that people are very, very struggling if they learn a programming language, and that programming language contains regular expression, because then regular expression is just another new programming language to learn when you're learning another programming language.
But then again, it's a very simple language, isn't it?
No, not really.
So sorry, why not put it into a workshop topic about regular expressions and forth?
And maybe a
Do we
strings.
need them?
Yeah, strings as well.
Strings.
So yeah, we can talk about the whole shebang.
Yeah.
It's a good way of extending the discussion there. I have to say, when I saw standardization of anything there, I thought that was a little optimistic,
Oh yeah.
given our community here. But thank you very much indeed, Anton.